Okay, can you guys see my screen? All right, so let's get started. So today we're going to discuss questions regarding serial interfaces, and there are two primary questions at this point. One is, let's understand why we need different encoding types for serial communication, like NRZ, NRZI, and the second question is, let's walk through what's the difference between serial versus parallel and how bits are actually getting pushed across the line over there. Right. So the first question we can just start with, as we would be walking through the lecture over here, where we really are looking at, what are we trying to do when we want to push a bit, along a line, a wire, right? So we have our digital, version of what information or data we want to send across a wire. But when we send that data across the wire, it is actually being sent as an analog signal, right? It is some energy that is being generated by the source, and that energy is basically pushing these electrons along the wire, and that's going as a frontier or a wave across the wire. And then when the receiver receives it, the receiver says, okay, well, I've captured, here is some kind of waveform, and it has to basically capture the energy from that waveform. You can think of capturing energy as a capacitor on the other end and saying, well, how much charge did I get in the last, time step, for example, or whenever this start of, some kind of analog wave was coming in, like that, right? So it does not know, whether it's a 1 or a 0 yet, like that, right? So and so you can say, well, what's the objective of sending anything over a wire? You want to just say, look, I want to send if I want to send a 8-bit message across, I just want to send 8 bits. I don't want to send too much more. I don't want to send, I don't want to have too much overhead, because if I just send the message across with minimal overhead, then I can actually get the highest throughput from that line. And so I want high throughput. And at the same time, I want to make sure that even if I get high throughput, when the receiver gets the message, the receiver is able to decode the message correctly. So minimize the receiver error, that, right? So you could have high throughput and high error, and that's really bad good put, right? So good put is just another way of saying, well, you sent me a lot of information, but there were a lot of errors through it. And this is the limited amount of information I could extract out of all the garbage that you sent, right? So now, but now then you can say, well, I'll send you some information, but I will also tag that information, put it in a way that actually can improve the way the receiver can receive it, right? So say, for example, I could send you information where I just send you a 0 as a 0 and a 1 as a 1. And if I want to send like this data stream across as a 0 1 0 0 0 1 1 1 0 1, then I would just actually send the signal like this, right? This is my digital signal. When it actually goes across the line, it is being sent as an analog waveform, which is some kind of the approximation of this digital signal. Like it could be taking some time to rise up here, be taking some time to fall from 1 to 0. It's not going to be like instantaneous like that, right? Because there is some kind of impedance and some kind of inertia in the actual medium that does not allow you to do something like an instantaneous change in the energy state of the medium itself, like that, right? So, but very simply, a high signal is a 1, a low signal is a 0. And but now the problem is that suppose I have like back-to-back zeros or back-to-back ones, then the receiver, first of all, is saying, okay, you're sending me supposedly some digital signal, because that's what we agreed upon before. But it does not, in order for the receiver to know exactly when this 0 ends and when the next 0 begins, it's becomes harder and harder, because in the ideal world, the sender and the receiver are totally synchronized. That means the sender says, hey, this is beat 1, this is beat 2, this is beat 3, and beat 4 and beat 5. and the receiver says, yep, got it, we are totally in sync, but in many protocols, the sender and receiver, they're obviously operating on different clock crystals, and they're operating separately from each other. They're operating at a distance. One could be in a hot location, one could be in a cold location. So their crystal could be going slightly faster than the other. Even if all of us had, we bought the same type of a 16 megahertz crystal, we all will not be operating at exactly 16 megahertz, right? You'll be going at say 16 megahertz plus say 20 hertz. And I'll be say maybe going sometimes at, because it's a little cooler over here, for example, or because of uh, the actual manufacturing, imperfections that are introduced, um, or because of the variability in the material of the crystal, I could be operating at 16 megahertz minus, 20 or 30 hertz at some time, right? So that causes me and you to not have exactly the same synchronization, the same time step. So, and
may I quickly ask a question to this?
Yeah.
Just to clarify, do we have a data line and a clock line that is telling basically the receiver of the data when to latch in the data, or how's this working?
So you do not have a clock line over here. All we are doing is just sending in the data. All you have is just this signal.
How does it figure out how fast the sender is running?
So that's what when we have, like, say, your serial communication, right, where you set the baud rate. So we have already agreed that, look, I will send you the data at 115 kilobauds, and I will format the signal where I have a start bit, I have a stop bit, and I do not have any parity bits. So then you're saying, okay, well, you have your data, you have an additional bit and an additional bit. So you have, for every byte of data, you essentially have 2 additional bits over there. So you know the format of the data and you know the speed of the data. And so as soon as I start sending it to you, you're saying, okay, well, the first bit was a start bit. Now the second, third, fourth, fifth, sixth, seventh, eighth bits are the data bits. And then there's a stop bit. And I know the rate at which the bits are coming to me. So we have basically agreed offline that
But
this
what if you're off by half a clock cycle? Do you take a 0 or a 1?
That's exactly the problem. That here we are essentially using the signal, like when the signal has a transition, we're using that transition to say, aha, the signal I'm receiving has switched from 1 to 0, and therefore I know that this is the end of that bit. So we are using that as a way for me to, so suppose you're sending me this data, right? The first time you send me this 0, I say, okay, well, that's a 0. And I say, I'm just basically counting 0, 0, 0, 0, 0, 0, 0 till this point. And then you basically send me a 1. And then when we have this transition, I say, great. Now I'm getting a different kind of different energy from the signal. And therefore I treat that as a way to provide me some feedback that this is a clock boundary. This is a bit boundary over there. So in some sense, we are kind of tying in the signal itself and the timing of the signal with the signal. And here the whole point is exactly that, Peter, that if I have the signal, but the signal has repeated repetitions of the same value, then I cannot give you the side information of the timing. Okay, so I cannot tell you, oh, here is a boundary. So I just have these gray lines drawn over here just to show you here's a boundary, here's a boundary. But when I receive it, I may be like 30, 40 hertz or 100 hertz or 200 hertz slower or faster than you. And maybe I just detect that right over here that, oh, that's the end of a bit. And then I start the next one over here. And then, so that just means that your clock and my clocks are offset by some rate, right? But clocks can have other problems. Who can tell me what other problems a clock can have? So one is an offset, that, what is the start? The offset just means that this was a start of the transition from a 0 to 1. And I just detect that start a little later because it took some propagation time. You're sending it from, where are you at now, Peter? You're across the world, right, from us? Yeah, so you're in Switzerland, right?
Yeah. Yeah.
Yeah, so it took few like it took few 100 microseconds to get from where you are to West Philly. Okay, so that causes some offset, and I do not know where you are versus where ASAP is versus where anyone else is a priori, right? And I don't know what, even if you are sitting next to me but you're using like a crappy Comcast network, it could introduce a lot of delay like that, right? So that's one. So that's an offset. What are other kind of problems that we could have with our crystal and our timing?
Maybe varying frequencies.
Yeah, so we could have different frequencies, right? And that is called like, and so it just means that I'm running at 16 megahertz minus 20 hertz, and you are running at 16 megahertz plus 20 hertz. And so therefore you are running, you're always running faster. If we both were running a race, after 1 minute you would be slightly ahead of me in terms of time, because you are basically counting time much faster than me, right? And I'm counting time slightly slower than actual time should be, like that, right? So what is actual time? It just means it's the wall clock time, right? But you as a microcontroller and me as a microcontroller have no idea what's the wall clock time, because we aren't synchronizing. But like say I have a MacBook here. The MacBook, every time it wakes up, it goes and talks to the network time protocol, and it syncs with this global network time protocol, and or with my phone, right? If I have like if you have a GSM phone, then the GSM phone will go and talk to that, or a CDMA phone, doesn't matter which network. The network will basically send your phone the time and say, oh, look, it's 12:36 now. I don't have to set that time, because the network really wants to maintain that time, right? So that is, so you having a slightly faster clock and me having a slightly slower clock means that over time, that means over 1 hour, over 1 day, over 10 days, we basically are at very different, we have counted time very differently, and we are actually very, very apart, right? So we have clock drift between us. Your clock is drifting at a faster rate and I'm drifting at a slower rate. And we are just saying that this drift rate is steady over time. Like so clock offset is one problem, clock drift is another. What are other issues? They were there later in the slides also in this lecture.
Noise.
So noise is there. Noise is basically a fact of life, right? I mean, you're going to have noise wherever you go, and what you need to ensure is that your receiver, when it receives any sort of message, that for it to decode that message, it has to have a good enough signal to noise ratio, and that's where the Shannon's theory comes into play. It's basically asking, it's basically it's come up with a very simple way of saying, well, what is the signal to noise ratio you need to have, say, 1 megabit per second on this line, or 10 megabits per second? Why can't I send like a gazillion megabits per second on the line, right? That's because the line itself is not going to be able to take the gazillion bits per second. And why can't the line take that, right? Because, and we can look at that question later on, but noise is basically just telling you that you cannot send the information faster than a particular rate for a channel given its signal to noise ratio. Uh, so let me give you an example of noise and limiting of a channel, right? So there's a great book that was written by this science fiction author Arthur C. Clarke called How the World Became One. I read it maybe many years ago. Yeah, I think when I was doing my undergrad. And basically that was a story of how they set up the first transatlantic line to send telegraph messages, right? And they were basically taking this line all the way from New York to some parts in Canada to Greenland and then to UK, uh, and laying this cable across the ocean and through all the crazy waves and the storms in the ocean for the first time back in, I think it's around 1880. Okay, and it was also, for any Wharton MNT people here, it was the first joint stock company that was funded, by JP Morgan, and they raised over $600 million. Imagine $600 million back in 1880. Okay, that's a lot of money today, right? So, and what happened was they were taking these cables and trying to put them through like and rolling them off the boats, and the cables would go maybe like 1,000 kilometers into the ocean or 1,000 miles, and then the cable would snap, and then they would have to come back all the way again because they can't fetch that cable from below like 2,000 meters under the sea level. It was just too deep, and the cable would keep snapping because there would be like very huge waves, and there would just be a lot of tension with as they were laying out the cable like that, right? So eventually in the third attempt they actually laid out the cable and they got it to go across transatlantically, and then they started to send the first signal. And what they saw was a transmission line problem, that you would send a 1 and then it would go all the way, across the Atlantic, and it hit UK. But then after it hit UK, it started reflecting back. And then they started reflecting back. And so then you had to wait for the reflection of that 1 to happen. And then you could send the next bit. So effectively that basically halved the throughput that you could have had with that line to begin with. So the line had only a 50% theoretical max throughput because of this reflection happening. So they had to figure out, okay, how do we deal with this transmission line problem? Then they basically started feeling all the pain that, then Shannon was able. And Shannon actually did this as part of his PhD thesis when he was, I think, 23 or 22 or something like that. And his PhD thesis, I think, was just about like 60 pages. That's it. And he was like, and to a lot of people who are interested in like doing theoretical work, everybody wants to have a Shannon like thesis like that, right? Because whatever Shannon came up with in his Shannon's law for the capacity of channels is like basically describing like Newton's law, but it's actually describing why it happens, right? So Newton's laws basically just describe what happens, but it doesn't say why gravity exists and what is gravity. It just says this is our observation of gravity. But Shannon's law is much more fundamental than even that. So we have offset and we have drift and we have noise, right? What other things are there with signals then? So you could have some, go ahead.
Oh, sorry. In the slides, it said something about how if you have like a long string of zeros or ones, you'll like change the average value of of the signal coming in. And I didn't understand why any receiver system would use that to parse signals, because why don't you just like, I mean, I guess, yeah, you don't know the ultimate voltage it's supposed to come at, but like,
yeah, so the reason why you have that, so in this slide, the problem is that we do not know the bit boundaries over here explicitly because we have no change in the signal here and we have no change in the signal here. So we need to have enough changes in the signal because we are trying to communicate both the data and the timing, right? In the next kind of the question that you raised over here is that, okay, well, I could do this and I could start to introduce some kind of changes in my signal. That means whenever I have a 1, I'm basically going to treat the 1 as a transition. If I was low, I become high. If I was high, I become low. And then I keep doing that. Right? So 0 basically says no transition. 1 says transition. So whenever you have a 1, that basically is always forcing a transition, and a transition is a good, way of providing feedback of the bit boundary or a change in the state of the system. And this baseline wander problem now is saying that, well, if I have a balance of 1s and 0s, then the average, you can just think of, okay, I'm changing every time I get a 0, I'm getting like a low voltage. Every time I get a 1, I get a high voltage, low voltage, high voltage. And so if I'm oscillating between that, I stay at my baseline is just saying that this is the average that I have, and I'm going above and below that average. But if I have like a 0 for too long, then then my average starts to go down. And why do we have this average, right? So what is this baseline? It's just saying that, look, on the receive side, there is some analog circuit over there that is looking at what is the change in the value, right? And there is more inertia in if I have back-to-back zeros and then have a one, because then that system does not have as much charge. In fact, the charge keeps getting depleted from that system. Now you'll say, well, in an ideal world, I do not have this baseline wander. But in the practical world, in an actual circuit, you have this because there's no way for the circuit to keep resetting and saying, oh, well, let's go back to a 50% baseline, because at the next boundary, I could get, a one or a zero. So then the circuit would actually have to have a reset sort of mechanism in itself at every bit boundary. And implementing that reset kind of circuit to say, okay, well, so far I've got a 1, 1, 1, 1. If I have many zeros, then I do not have enough energy in the circuit. So the energy in the circuit basically is depleted in my capacitor to say this is what my baseline looks like. So then I'm just comparing, is it a 1 or a 0 to this baseline? And every time, so the baseline keeps going lower and lower and lower because I have too many zeros at this point. And then anytime I have a transition, if the transition is above this baseline, I just treat it as a 1. So but then you can say, look, in theory, I'm going to just be comparing, is this voltage above or below? If I have 0 to 5 volts, is it above or below 2.5 volts? But in practice, you're actually comparing to what is an actual value in a capacitor that you can have, right? So you would always want to have this, like how we did with our ADC. We're always trying to compare to some generated voltage of 2.5 volts. Here, because these circuits operate so fast, that much faster than an ADC can generate, a voltage, they have to use the average of the value based on the signal. Again, the main problem is that we just have only this signal to provide us, timing, but we also have only this signal to provide us what is a good comparison of what's a high and what's a low. I can't generate like an ADC input and say, hey, here's 2.5. Then you can say, no. How about I just permanently just generate 2.5 volts on the receive side and keep comparing to that? If I even run that comparison, I won't be able to keep up with this rate over here, right? So we can keep taking that argument forward and saying, how about I make like this comparison really efficient? Then I say, yeah, then definitely, sure. But in reality, we're not going to get a clean 0 or a clean 1 on the line, because the line itself is not sometimes going to go all the way down to 0, and it's not going to go all the way up because the line is lossy. And so that's the issue over here, right? So again, we are trying to compare, we're trying to get timing, and we're trying to get what is a good discrimination of high and low from the same signal. And going back to Peter's comment, like, okay, wait, why don't we just solve this problem, and this clock recovery problem where, the sender is sending at this clock rate, but the receiver has slightly different clock rates because the receiver says going faster or slower. In this case, the receiver is going slower than the sender. The receiver's, a bit count over here, the time for a bit is larger than the sender's, and it's also offset, right? So, but it's also not offset the same amount, right? So sometimes it is offset a little, sometimes it's offset a more. So from bit to bit, I'm just offset from you slightly, every time. So that is called jitter over here, right? So that means you are jittering and I'm jittering. And while we are jittering and I'm saying, okay, I'm going to start now, like we started this class at 12:05. So 12:05 is an offset. That means because that 5 minutes is lost permanently, and we just started what we should have started at 12, we started at 12:05, right? And we do that for practical reasons, but that's called basically an offset. Now, when you rewatch this video, or if anybody else is rewatching this video, you watch this video at 1.8 times the speed. I don't know, what's a good speed you guys watch videos or listen to audio at? Do you listen to it at the same speed or
1.25 or 1.5?
So 1.5, like something that's faster than that, right? So So when you watch, so then in that case, you're basically your clock drift is at 1.25 like that, right? So even though the original was at 1, your basically your clock is going much faster than that, right? But what if you watched it, at 1.25, and then when it got really boring, you went to 1.5, and you're like, yeah, I know this stuff and I can understand it. And then when it's really like something that you're not clear about, then you go back to 1, but you keep changing the rate, right? And so that means you have a lot of jitter that you've introduced in how you are actually consuming the content. And that is a big problem, and you can't recover that because both the sender is jittering and the receiver is jittering, and there's no easy way to actually know what the boundaries are over there, right? So then that basically brings us to the next part and says, okay, wait. So in order for me, like in this case, we came to half a solution that whenever we have a 1, we introduce a transition. We are forcing a transition. And that means if I have a back-to-back 1 over here, I have a transition. And then we can say, hey, so what we really want is a signal where we always introduce some transitions. So if I have all zeros, I will just map that to a slightly longer, bit vector, but I will actually introduce a lot of transitions over here. Because whenever I have a 1, transition, no transition. So here I basically had no transition, and here I have a lot of transitions. So I map whatever I have to a larger number of bits. So from 4 to 5 bits or from 4 to 8 bits. And therefore I'm forcing the number of transitions because I'm going to map it to a sequence that has, by default, at least that much or more transitions than the original signal, right? Because transitions are actually communicating that information. The side effect is, okay, I have more bits now. That means my efficiency actually goes down, right? I have, if I encode 4 bits into 5 bits, I only have 4 out of 5 bits that are the actual information, but my whole bit encoding over here is one group, right? It's not just that these 4 zeros became 4 ones. The 4 zeros became this whole thing together. So I have an 80% efficiency in transferring information like that, right? So, but the data bits have increased over here, right? So, so another version. So then, as we went through time, they said, well, what we can do is we can actually, we have this clock that is over here, and we have our data. And if I run my clock at twice the speed of the data, and I just XOR it, and then I can basically now have a transition in all my data bits over here, right? So that means a 1 will basically be going from low to high, and a 0 will be going from from high to low, and so on, right? So so that's essentially the issue over here, right? So turn on this light. So so in this case, we have a transition with every bit over here, right? But what is the cost we have to pay over here?
Efficiency.
Yeah, so again, efficiency went down to 50% because now I actually could have sent this same data stream at the clock rate, right? Which was what I was doing before, but now I'm sending it at half the clock rate, right over here, right? But I'm actually introducing a lot of, so we say, okay, efficiency went down by 50%, but effectively, how much did it go down by 50%, or is it actually better than if I sent you some message and you couldn't interpret the message, and then you say, hey, I didn't hear you well. Can you say that again? Can you resend that packet? Now for me to resend that packet means I have to repeat all of that information again, right? So which is more efficient? And that's something that as an engineer, you got to keep trying to figure out how to balance, right? Do I send you a lot of high-speed data that is very corrupted? Or do I send you slower data that is not as corrupted? Right? So it's a trade-off, right? So between corruption of the data and between how efficient I can have with that data, right? So that just, and if you go to like, what does Shannon's law say? Well, let's start with when I send a bit, I basically have a probability that that bit is centered around 0 over here, right? And so this is say like a Gaussian distribution of sending, of a particular signal, right? And it has this kind of variance over here. And that's the density function of the Gaussian distribution. But I also have some noise, right? When I send you a signal, the receiver basically gets the original signal plus the noise, and the receiver has to be able to extract the signal from this combination of the signal and noise. So if I send like, a signal, say that is a 1, that could have this distribution. But if I send a signal that has a 0, it could have this distribution. So there is a non-zero probability that this 1 can get interpreted as a 0, and a 0 can get interpreted as a 1. And that's sort of the root of, where the signal to noise ratio really is coming into play. Why are they overlapping? Because this is just saying that, well, if I have a lot of signal, if I have a very high signal to noise ratio, that means the noise is very low, and therefore this overlap over here is very small, or no, it's not even overlapping, right? But if I have a lower signal to noise ratio, then I have much more overlap between, my signals actually getting mixed up. And so you don't have to understand like, you don't have to understand this math over here, but the math is basically just there to give you an idea of, how do you actually extract, probability of, a bit getting flipped, and how do you do that based on, the actual probability of whether, a bit is going in as a 1, or what is the probability that the bit actually gets flipped on the channel, right? So even how does the bit get flipped on a channel? It's just that when it is going through the channel, the noise is so large, and the noise is sort of non-stationary, but normally we treat the noise as like additive white Gaussian noise. That means it's basically following like a Gaussian distribution itself, the noise. So at the tails of the distribution, you could have very large amount of noise, and that could cause the bit to actually flip and be observed by the receiver as a 1 instead of a 0, or as a 0 instead of a 1. So, well, long story short, for a signal processing course, you would really want to understand and be able to derive, given the probability of error, and what is the noise ratio, what is the probability of, having a bit flipped. And the channel capacity theorem over here essentially is just saying that, well, if I want to know, well, for a channel bandwidth that I have, say Verizon is given like, 1 megahertz of spectrum, but in the 1900 megahertz band, then they know, okay, well, in an urban area, this is the amount of noise we normally have. Sometimes we have a lot more noise. They know what is the noise distribution, and then they need to figure out, okay, well, how much data can we send, right? So why is the integration going from D to infinity? In that, you mean in the previous one? Yeah, I mean, it's going from basically D to infinity because, this is a long tail distribution, right? This is asymptotic to the floor over here, right? So it's a long tail distribution. It does not like truncate at this point, right? A Gaussian distribution will go till infinity, right? Okay, so I'll skip over like the channel's capacity, but basically with this example, you can see, okay, well, given the average noise that we have on this particular channel, then we can actually figure out, well, what is the maximum throughput that I can have on the channel, right? And this is a big question that all like, data providers provide, right? I mean, because they want to tell you that you're getting like 4G and 5G, and or that you're getting 100 megabits per second, and they want to charge you according to that, right? I mean, that's how they say, well, because faster the bit rate means more data you can download, and in general it means that you have also lower latency, right? Although latency and throughput are not necessarily, they don't always have to be correlated, but at least, so if you want to download like large torrent files, then that's better, right? You want high, or you're a gamer, you want to have a low latency line more than high throughput. So this is basically just a fundamental theorem that says, well, if you do know, what is your noise distribution, then for a particular channel, then you can actually get a very, you can get the theoretical maximum data rate for that channel. And this was the whole reason why we switched from, twisted pair copper wires for communication like Ethernet to optical lines, right? Because optical lines have much lower signal to noise ratio, and therefore you can actually have a much higher throughput on those. They also have a much larger bandwidth, right? Because you could send across a wider spectrum, and therefore you could have like orders of magnitude more data going across an optic fiber line. Compare that to wired versus wireless, right? So with wired, your signal to noise ratio is say about 10 to the negative 12. That means 1 out of 4 million bits, you basically have 1 bit flipped on average. But with wireless, the signal to noise ratio is closer to like say 10 to the negative 9 or 10 to the negative 8. So that's like 4 or 5 orders of magnitude higher noise than a wired line, and therefore we do not have like 100 megabits per second being shared. There are other reasons which we'll come to in the next few lectures of what are the challenges with wireless, but that's that over here. So let me fast forward from these slides to the next part, right? So serial versus parallel. So serial means exactly that, right? It just means that if I have 8 bits to send you, but I only have 1 line to send you that, I'm going to send the 8 bits one by one to you, right? If I'm in parallel, I have 8 bits to send you and I have 8 lines, I can send you all 8 bits in one shot, right? In one clock cycle, you get all 8 bits because you get each bit on one line over here, right? And that's why, we switched from, 8-bit microcontrollers to 64-bit, processors, because 64-bit processors can get, data across from memory to the CPU much faster than that, right? So, but what is the cost for that? The cost is that you have to have more pins. That means you have to have more physical space allocated to that, and space is always a premium because we are trying to make these chips as small as possible with as few pins as possible, because that allows us. So why do we want to make chips that small? Like, why do we want to limit the number of pins? Why can't I just have like 1,000 pins and make like a big ass chip like that, right? It's just a common sense question, but you need to know some, like, why can't we like just say, why don't we just have like a 2-inch by 2-inch chip over there?
It's not useful for commercial applications.
That's like a good business answer, but I don't know why it's not useful.
Does it have to do with crosstalk?
Crosstalk.
Between the pins? If you have like a bunch of high frequency signals next to each other?
That could be, but if you have fewer pins and you're sending the signal in a serial line, then I could be sending the bits too fast, and they could be having inter-signal interference. That means between one bit to the other bit, they basically are overlapping each other, because there is some impedance in the channel itself. The channel is not like at the same density, and the receiver also is receiving, like in a wireless channel, you're getting the signal that is bouncing off this wall, that wall, and then coming there. You have signals that are coming directly to you. So the signal is not coming at you at exactly the same time. It's coming at you over some time. And if that time is a little too long, then, and I send you the next signal before you received all the energy from the first one, then I have inter-signal interference. So yeah, there could be crosstalk because I have many lines. So crosstalk could be one reason. The first answer also is valid, that you know, if I have like such a big chip, I can't fit that into like a little, you know, Apple EarPod thing like that, right? The Apple EarPod by construction means that, you know, you have to have a really, really tiny chip to follow. But what's the fundamental reason, right? What's the physics reason? Crosstalk is a physics reason, but what are other physics reasons that basically say we do not want to have a very large chip? Like why is the whole digital industry trying to get to smaller and smaller chips, smaller and smaller, fit as many more transistors in the same size chips?
Power, more energy
Power.
efficient.
So but more transistors mean more power.
But I guess if they're smaller, they consume less power.
If they are smaller, they use less power, but they also have more leakage. That means they are also leaking power a lot more. So the answer is yes and no for that, for power. Yes, yeah, if you have a larger die size, you have to power on bigger transistors, and bigger transistors will consume more power. So that answer is also true, but the main problem is that, you know, like when you basically are fabricating silicon, then, you know, you have a certain output in a yield of the silicon actually coming out to be pure silicon without any basic impurities, right? And there's a probability of an impurity. So the larger the area you go to, the higher the probability that you have impurities in that die size, and then the yield goes down. Okay, but the yield, it just means that Intel makes like a 1 million chips, but out of that, you know, not all 1 million chips are perfect. Some of them actually, like 800,000 of them are actually, you know, good for sale, but the other remaining ones, they can't run at 4 gigahertz. They can only run at 2 gigahertz because at 4 gigahertz, they have too many impurities and you have a lot of wrong computations happening. So then they have to sell the remaining 20% as cheaper chips. So instead of charging you $1,000 for the 4 gigahertz chips, or let's say $100 for the 4 gigahertz chips, they can only charge you like $60 for the 2 gigahertz chips, like that, right? So the yield basically goes down, and therefore you want to have smaller die sizes, and therefore you want to have, you know, fewer IO lines, because the IO lines have a minimum sort of, you know, size that you need to have to prevent crosstalk from happening. And also, the more lines you have, it just means that you need to have more senders and receivers pushing out the energy from these lines, like that, right? So you need to power on more of these pins over here. So let's look at what happens now when I have a serial. Suppose this is my buffer, right? I have 0, 1, 2, 3, 4, 5, 6, 7 in my transmit buffer. And then in the first, so I'm ready to send now, right? I haven't sent the receiver anything. Then I basically push out 1 bit, and then the receiver receives 1 bit. Then I push out the next bit, the next bit, the next bit. With each clock cycle over here, I'm basically pushing out 1 bit. So every time I get a clock, I basically say, okay, send the next bit, send the next bit, send the next bit, send the next bit. And I'm sending that. Now that clock may not be shared between the transmitter and receiver. It's just the clock that I have. When you receive something, then you also have a clock, but that's your clock, right? We are not synchronized necessarily. We could be synchronized, but in this case, we are not synchronized, but I'm just sending you bit by bit by bit by bit. So basically this is my buffer, and I'm just sending you 1 bit at a time till your buffer gets full and my buffer basically gets empty. Once it's empty, then an interrupt is raised and said, okay, I sent the packet. Once this buffer gets full, it says, okay, I received 1 packet. And that's what is done over here, right? So another way to look at it is to treat it as a shift register, right? A shift register is a very simple thing that basically you have your register over here, which you're saying, okay, put your data in this. And then after that, it loads this data into a single shift register. And then it starts to basically push the bits out 1 by 1 onto this transmission line. And this transmission line goes to the receiver and then puts basically bit by bit onto that, right? So this is a serial line. So it basically requires 8 clock cycles to, or 8 clock ticks on the sender to send the whole byte across to the receiver, right? If we had a parallel line, it would just require one clock tick to send all 8 bits across over here, right? So does that answer that question regarding, serial versus parallel? Or you had another related question to that?
No, I'm good.
Okay. So any other questions then? We still have 10 minutes if you want to use that for other questions. I'll just, so essentially what I wanted to cover
I still
today.
have a question. Oh, sorry.
Yeah.
I had a question concerning the parity bit. I didn't quite understand how that worked. There's like this story of basically placing a bit if there's like an odd or even number of ones in the signal.
Okay, so the parity bit is basically, it's just saying like, okay, if you sent me some message, can you also send me some way of telling me what I should expect in that message? But you only have one bit to tell me that. And then by saying that, you basically say, okay, well, I'm just going to tell you that you should expect an even number of ones. And I'm like, okay, that's better than no information. And so then when I receive the message, I just count the number of ones and I see if it's even, I say, okay, at least it seems to be satisfying that one additional piece of information you gave me about what I should be getting, like that, right? So the parity is basically a general class of, data integrity sort of mechanisms, right? It's like, suppose I send you now a 1 megabyte file, right? And then but I just tell you here's one parity bit, and this 1 megabyte file has 1 megabytes, okay, 1 million bytes, and that's 8 million bits. And when you count across all these 8 million bits, you should have an even number of ones. And you're like, okay, that is more information, but it's kind of not that useful, because what happens if 2 ones basically got flipped? And so not just one, so now 2 ones got flipped, and then I can only detect if one or a 1 0 got flipped in the entire 8 million bits that uh, you sent me, like that, right? So then that's not enough, right? So then we need to say, okay, well, maybe you should have a two-way parity, like that, right? And maybe you should have more parity bits that describe to you what. So then there are checksums, right? So checksums are different kind of data integrity. So that's like and so actually when I was a junior, I worked for that networking company, and my job was basically to implement like a most efficient checksum, or a most efficient way to basically say, here we've sent you like 9,000 bytes of data. How do you go ahead and check all these bytes and make sure that you received what we meant to send you, right? So, or another more precise way to say it is, okay, I sent you some data. How can you tell me if I have an error, right? How do I know if I have an error? If you gave me only one parity bit, then I know that I have an error if one bit was flipped, or if an odd number of bits were flipped. If an even number of bits are flipped, then I can't tell you anything. But then you say, okay, well, how about I give you like a two-way parity, right? And I think we'll do that when we come to wireless. We have a two-way parity, and then you would have like polynomials, actually, like you would have different ways of computing parity bits that are not just a single bit, but they would be many bits, right? So they're called like checksums, and essentially they go into a lot of like very abstract theoretical algebra to come up with these ways of figuring out how can we have the most compressed form of summarizing how many bits we have, what you should expect in these bits. Yeah, so CRC is called a cyclic redundancy check. So actually that was exactly my first project as a junior, was to implement a CRC 32 checksum, okay, as part of these network packets. And if you go and look on Wikipedia, what are CRCs, then they will actually show you, look, these CRCs are polynomials. Basically, they are ways to actually compute which bit should we XOR in which order, and how do we come up with, say, if I have 8 million bits, then I would need at the minimum like 32 bits in CRC 32 to say, if 32 bytes actually in this case. So 32 bits to give you a very efficient way of saying that this is what you should be receiving from me. Because when you receive a message, I send you the message and I send you this extra code, right? And what is this extra code? For a single parity bit, all that code is doing is it's just XORing the bits and saying, you should have an odd or an even number of ones, and therefore and that's what you would do. You would just receive your packet, XOR all the bits, and see whether you have odd or zero. With the CRC32, you would run this code now, and it's a little bit more complex code than just XORing, but it's a sequence, a different type of sequence of XORing which bits, and then you would actually check, okay, is my CRC based on the packet I received, I compute a CRC, and based on the packet you sent, you also send me a CRC with that, right? So then I check, is my CRC that I computed on the receipt bytes the same as the CRC that you sent me? And then I say, okay, that's good, right? So, but here we have like a problem, right? Look, whatever you send me can get corrupted, whether it's a data or whether it's a CRC, the channel doesn't really care, right? Data is data. And so in that case, even the CRC can actually get corrupted. So then the CRC also needs a CRC, or it needs its own checksum, and that checksum needs its own checksum, and then basically it just goes on forever, right? It's kind of like saying that, hey, did you get what I sent you? And then you say, I did, but maybe I didn't hear you. And then you say, hey, did you hear me? And then I say, I heard you, but I'm not sure whether you heard me, whether I said I heard you. And then you're not sure whether, and then we just keep going back and say, yeah, I got it. And they're saying, okay, you got it. Is that what you said? And I said, yeah, that's what I said. I got it. And they say, did you actually say that you got it, And then we just keep going back and forth because we're just acknowledging each other forever, right? So we will cover parities in a little bit more detail when we come to wireless, because in wireless you need more parities. But here, this is just saying that for the serial communication protocol, as part of the protocol, there is a parity bit over here. And the parity bit is basically just taking all of these data bits and XORing them. And then you would add that parity bit as part of that, right? So you would have your start bit for sending a serial communication. You would have your 7 data bits. Then you would have the parity bit that is computed over these 7 data bits, and then some stop bits. But basically these are kind of delimiters to saying that, hey, I'm sending this new packet. This is a start bit for that. And then it's saying, here are all the bits. And it's saying, okay, here's the 8th, the 9th bit that you get is a parity bit. The 10th and 11th bit that you get are basically just saying, stop, this is the end of the packet, like that, right? So just a way of communicating that this packet is kind of self-contained. And this, it's sort of like every time you get this, you have the same format and the data is within that format over there. So hopefully that answered a little bit about parity bits, maybe a little bit more, but than you asked for. But we'll cover that again in the next week with wireless communication. Okay, any other questions? Okay, so for the quiz, essentially you'll have questions on concurrency. So just follow through that lecture, rate monotonic scheduling, and basics of EDF, but we didn't go into EDF in more detail than just the basics of EDF. I think just about 16 slides in the EDF lecture. And all you need to know is, how do you know whether some task is schedulable or not, and just variations of that, how to use mutexes and semaphores and variations of that. Okay, any other questions? Okay, all good? Happy? Okay, great. Okay, if you have any other questions, okay, yeah, go ahead.
I'm still kind of confused by the Gaussian distribution. Like if the error occurs between d plus and d minus, like how, like why would you do integration going from d to positive infinity?
From, you mean in this case here?
Yeah, right. Because like your high is plus d and your low is minus d, right? So anything, if there's an error due to the noise, you should be arriving like, yeah, that overlapping part from 0. But when you calculating probability of error, why is the integration of a Gaussian distribution going from d to positive infinity?
So that's basically just saying that, you know, I have absolutely, I'm absolutely sure that, you know, my let me just see this fully. So it's a probability of error, probability that whatever I get is less than 0, right? And I'm integrating from d to infinity in this case. And so you're saying that, okay, well, why are we integrating just from here to infinity, right?
Right,
Is
yeah.
that your question?
Yeah.
Yeah. So in this case, I want to know, basically what I want to know is, okay, so it should be like you're going from, okay, so D is symmetric over here, right? So so I have from 0 to D and I have from 0 to D minus D.
Right.
And essentially I'm trying to compute, you know, what is the probability that, you know, this signal coming in is going to overlap with, you know, a sure signal that I have. I know that, you know, let's see, one second. I just, it's been a while since I saw this equation. Okay. Okay, so I have the variance also over here as part of that. And
oh wait, I think it sort of makes sense because the Gaussian distribution have a mean of 0. Now, if we're shifted by d, the error actually occurs between somewhere of like going from negative infinity to d, and it's like symmetric, so you can flip it to d to positive infinity, I think.
Yeah. Did everybody understand that? Okay, that's a good. Yeah, and so essentially this is one way. This Q function is essentially measuring, you know, what is the probability of this error, right? That is crossing this, right? So, all right. So any other questions, guys? All good? Okay, yeah. So if you want to read up more on this, this is basically called the binary channel channel for with errors, and that's like a common problem. I can share a link also, from just a quick link for you to get an explanation for this, for what is this basic, how do you understand noise and the effect of Gaussian noise on a channel. Okay, so I think we'll stop at this point over here, and if you have more questions, just ask away, and others we can